Professor Umit Ozkan from the Ohio State University, and Umit has been also a chair at the North American, preparing for the North American Catalysis Society meeting, and I can assure you that she has poured her heart and soul into getting this meeting organized. She has been elected a fellow for a number of organizations, including ACS, AICHE, and the American Association of Advancement of Science. And her talk will be Investigation of the Board Effects on Cobalt Coordination Environment under in situ Reforming Conditions for Bioderived Liquids. Please help me welcome Professor Ozkan.
Thank you, Ashik. I'd like to start by thanking the organizers for inviting me to this symposium, special symposium honoring Burt. I really feel honored to be included in this group of people celebrating this event. Can you hear me? Or now? Is that better? Okay. Also, it is very special that at least two of my co-organizers for the next NAM meeting, 23rd North American meeting of the Catalysis Society, are here with me. Also, our honorary chair, Burt Davis, who has been guiding us and giving us a lot of moral support, which we see to be. When I think of Burt, what comes to mind is modesty, humility, always an open heart to help, especially the young people, encouragement. In addition to really being on top of his craft, he has always remained very humble, very down to earth, very approachable, and it has meant a lot to many of us who really look upon him as a role model. Also, Burt has given a lot to the Catalysis community in terms of service. He has served on the board of North American Catalysis Society for many years as a secretary, including also in other roles. He has served American Chemical Society, especially the Petroleum Chemistry Division, in various leadership roles. And of course, he has been the historian of the Catalysis community, not just for his country, but for the whole world. He has been taking pictures and videos of many different speakers over the years, and now he has an incredible archive of the history going back many, many decades. In fact, North American Catalysis Society is really trying hard to organize it so that all of that record remains for the generations to come. So, in addition to being a great researcher and putting his signature on energy research, he has also been an incredible servant to the Catalysis community. So with that, again, Burt, congratulations, and thank you for everything you have done, and I'm proud to be here to congratulate you on this occasion. So what I'm going to talk about today is related to ethanol steam reforming over cobalt-based catalyst. We are focusing on serious force in this talk. Actually, ethanol steam reforming is a if you look at it, it may be deceivingly simple. If you just look at it, okay, ethanol and water giving 6 molecules of hydrogen and CO2 is still simple enough. And if you look at the reaction products under thermodynamically controlled conditions, again, everything looks pretty straightforward. For example, in this window of 400, 500 degrees centigrade, essentially everything is going to hydrogen and CO2. There isn't much CO left, there isn't much methane left, and none of the intermediates or side products are appearing in this picture. Also, if you look at the coking picture, for example, if you use high enough water to carbon ratios, as you can see here, there is really that much carbon formation. But this is a thermodynamic picture. The kinetic picture is much, much more different and a lot more complicated than this. So actually, ethanol steam reforming is governed by a complex network of reactions catalyzed by different types. Some of those reactions help the hydrogen yields. Of course, ethanol steam reforming, ethanol dehydrogenation, acetaldehyde steam reforming. Acetaldehyde is an intermediate. Forward water gas shift, methane steam reforming. Again, methane can be a side product or an intermediate. These all help the hydrogen yields. But there are a lot of other reactions that create loss of selectivity. For example, ethanol decomposition, ethanol dehydration, which gives ethylene and then it leads to coking most of the time. Acetaldehyde decomposition, giving methane, acetone formation, reverse water gas shift, methanation. These are all reactions that we run into and they take away from the selectivity. There are also reactions that lead to coking. Once ethylene is formed, especially if the surfaces are acidic enough, hydration, dehydration becomes an important reaction, and once ethylene is formed, it goes to coke quite readily. Similarly, methane decomposition and Woodard reactions, they both may contribute to coking on the surface. So we have been doing research in this area for quite some time. It started with a Department of Energy sponsored program. So we looked at a lot of different things, looking at different formulations. We've done a lot of characterization. Of course, we coupled it with testing, some computational modeling, mechanistic studies. We were even forced to do some economic analysis. We really did that, keeping at speed. We weren't really willing to do that, but Joey wanted us to do. And anyway, so what came out of this is that these cobalt-based catalysts can perform in a lot of different ways, depending on many different parameters. The way we synthesize these materials, the formulation, the loading levels, dopants, the precursors that we use for cobalt, impregnation medium, whether it is aqueous medium or organic-based medium, pretreatment conditions, all of these impact metal dispersion, reducibility, oxygen mobility, surface acidity, basicity, metal support interaction, and support nanostructure. These in turn can impact activity, selectivity, and stability, which really comes together in what we call the catalytic forms. So many of these results were already published in various publications. I'm going to say a few words about the activation. Over some years of research, we really decided that, or concluded that there are two major modes of the activation. One is coking, and the factors that lead to coking is most importantly high surface acidity, because high surface acidity leads to ethylene formation, and then it just goes to coke. Low oxygen mobility, if we don't have enough oxygen coming to the surface or on the surface to gasify and oxidize the carbonaceous residues left on the surface, it creates coking. And also low metal support interface, because often that support is involved in replenishing the oxygen at the cobalt sites. So I will talk about how to prevent coking, because we have, I talked about it in some other forms. But another factor that impacts the activation is the sintering. And the factors that lead to sintering are low dispersion, low oxygen mobility, high operating temperatures, and then the need for pre-reduce it with hydrogen, because sometimes the sintering takes place during the pre-treatment. So we started looking into the need to pre-reduce with hydrogen, or if there's indeed a need for that. So I'm going to say talk about a few of the results looking at how cobalt species evolve from precursor all the way to post-reaction, and talk about the role of pretreatment. Just going back a few steps, if we start out with a precursor, so we're starting out with a cerium precursor and cobalt. If you're using a nitrate for the cobalt, for example, and if we do a calcination, we see that around 200 degrees centigrade, the nitrate is decomposing, beginning to decompose, and we see the nitrogen-containing species and also the oxygen consumption that corresponds to that, so that those are mass spec results. If we look at the evolution during calcination from precursor to the oxidized catalyst, this is looking at Raman spectra during calcination. So we can see the nitrate bands here very clearly when we start at the temperature, and they're still visible around 200 to 50 degrees centigrade. They start diminishing, and by 300 degrees centigrade, all of the nitrate has decomposed. We can also see the formation of the bands that correspond to cobalt species. This is CeO304 as a reference. We're starting out where we only see Syria, so at 25 degrees centigrade, we only have the Syria band. And nothing much happens until we reach around 300 degrees centigrade, and at that point we start seeing the bands that correspond to CeO304, and if you keep the temperature higher, CeO304 becomes more crystalline and the round bands become sharper. Now, if we are reducing it in situ, again here is CeO304 for reference, and here is Syria. We're reducing it in hydrogen, and there are two steps that are involved in reducing these cobalt species. The first one takes us from CeO304 to COO, and then after that we go to metallic cobalt around 400 degrees centigrade. And we can actually see this by program reduction. We're looking at the PCB signal for hydrogen consumption here. There are two very distinct features. One takes us from CeO304 to COO, the other one from cobalt plus 2 to metallic cobalt. And actually we can follow the same phenomena using TGA, and you can see the two reduction features very clearly here in terms of the weight loss. Now, we wanted to see how the cobalt species were evolving under steam reforming conditions. So these results are operando X-ray diffraction results. So we're actually taking diffraction patterns while ethanol steam reforming is continuing. And on one hand, we have catalysts which have just been oxidized but no pre-reduction. So this is the sample, pristine sample. We have CeO304 and Syria treated there, of course. And we're beginning to form cobalt oxide plus 2 around 350. And then as we go higher, we start seeing cobalt oxide. If we keep it at this temperature lower, for longer, we will end up with metallic cobalt. But usually, the steady state catalyst has a mixture of the two balances. What happens if we start out with a reduced catalyst? So here's the reduced catalyst. It is primarily metallic cobalt, very little COO. Something interesting happens. As we increase the temperature under ethanol steam reforming, cobalt, first we start seeing some reoxidation of the cobalt species, which was surprising to us. But as we go higher at temperatures, cobalt species reduce back, and we end up primarily with metallic cobalt species. We have looked at this again in different ways. We wanted to see if this reoxidation is due to diffusion of oxygen from the support. So we first reduced the catalyst in situ, looked at X-ray diffraction patterns, and then kept it under an inert at 450 degrees centigrade to see if there was enough oxygen coming to the surface to reoxidize cobalt, and the answer was not much. Most of the reoxidation is taking place because of the reaction media. And this is another, this time isothermally, we are continuing the reaction starting with an oxidized catalyst, and you can see on time on stream, for example, 1 hour black and then 12 hours red, and you can see metallic peaks are growing, oxide peaks are getting smaller. We also wanted to do some X-ray absorption spectroscopy. We have been collaborating with Dr. Jeff Miller at Argonne National Laboratory, who has been very helpful and very generous with his time, and he loves helping students. So we managed to get some mean times at the decimal time source, and this is actually the in situ reactor system that was really designed by Chris Marshall and Jeff Miller, probably. I don't know the exact source. But we are looking at the zinc spectra here. So these are true, actually I call them in situ, but this should really be operando. I think I have a little problem with these two terms, because when I was growing up, there was only the term in situ. So in situ meant under reaction conditions. Now in situ means something else, and then there is operando. So true reaction conditions is operando. So I still have a hard time using the term operando, so I keep using in situ where I should be saying operando. So this is operando, under true ethanol stream forming conditions. So we have the reference spectra here, CO3 or 4, and the sample spectrum is in black. So actually starting out we have CO3 or 4 only 100%, and then we have CO3, some reduction at 350 degrees centigrade, so we reduced it mostly to COO. If we raise the temperature further, there is hardly any CO3 or 4 left, very little, most of it is about +2. At 450 degrees centigrade, it's almost half enough. But as we keep going higher in temperatures, we have mostly a mixture of metallic cobalt and +2, but it is more metallic than +2. So this is starting with an oxidized catalyst and keeping it under reaction conditions and moving up in temperature. Now what happens if we start with a reduced set of reduced catalyst? Again, we have, starting out, we have mostly metallic cobalt and some COO, even because the bulk perhaps is not totally reduced. And interestingly, this is very consistent with the X-ray diffraction data that we have seen earlier. As we keep it under reaction conditions and raise the temperature, we reoxidize the cobalt species somewhat, so we have more +2 here. But as we increase the temperature and stay under reaction conditions, we reduce that, and then we end up again with a mixture of +2 and metallic types. And actually, if you look at the two samples, the one that was oxidized initially and pre-reduced, where we end up with is remarkably similar. So regardless of where we start, at steady state, we're ending up at the same conditions. We also looked at the X-axis region, and these are the reference spectra that were used for the fitting. And here at 350 degrees centigrade, oxidized sample versus reduced sample, even by just looking at it very quickly, you can tell that they look very different. Again, 400 degrees centigrade, they are becoming a little more similar. The cobalt, oxygen cobalt species are getting smaller here. At 450 degrees centigrade, and finally at 500 degrees centigrade, if you superimpose them, they look remarkably similar at 500 degrees centigrade. So regardless of where we start, we end up at the same point. How about the reaction performance? So we have done some work with that, starting out either with a pre-oxidized catalyst or pre-reduced catalyst. The red ones are pre-reduced, black lines are oxidized. And we're looking at either the formation rate or the CO2 production rate. And regardless of where we start initially, if we have pre-oxidized catalyst, the performance is much poorer. We don't have that much conversion. But as we go higher in temperatures and keep it steady state, we end up with essentially the same condition. again, the product distribution is also very similar. Starting out, product distribution, you can tell by looking at the colors of these bars, very different. But once we reach 450, 500, product distribution is essentially identical or very, very close to one another. So just to quickly summarize this phase of the talk, don't get excited, I'm not finishing yet. Cobalt species in purity catalyst we see undergo a partial oxidation during ethanol steam reforming. Cobalt species in oxidized catalyst undergo a partial reduction during steam reforming, and they really reach to the same oxidation state, the same coordination environment under reaction conditions, regardless of the pretreatment. And it also appears that at steady state, the cobalt species are in a mixed balance state, the mixture of metallic and +2, but there's more metallic sites. Now let me move on to looking at the support effect a little more carefully. So we have done, this is ongoing actually, look at the effect of the support morphology and effect of the particle size. Probably I will have time to talk about only one of them, so I think I'll start with the morphology. Of course, looking at different crystal morphologies is not a new concept. It has been done over the decades. Different crystal morphologies, the effect of different crystal morphologies on catalytic performance has been reported for not just only supports, but also for bulk oxides, including some of our work with molybdenum trioxide and vanadium-related catalysts early on. And then graphite carbon materials, again, some of our work in the oxygen reduction reaction. Looking at ceria morphology also is widely studied in different reactions. Water gas shift products, we looked at this ourselves somewhat, but there are a lot of others in the literature that you can see. So if we focus on the ceria crystal planes, different crystal planes allow for oxygen vacancies to perform to different extents. So the proposed model suggests that the surface density of oxygen atoms increase in this direction, and the energy of formation of oxygen vacancies also follow the same order. So on the surface, 110 surfaces are more likely to form oxygen vacancies, and usually oxygen vacancies are associated with increased oxygen mobility, which is important for especially for selectivity, but as well as stability purposes. So we're comparing two different morphologies here. I picked two significantly different morphologies. On one hand, we are forming nanorods, and on the other hand, we are forming nanocubes. If we look at some TM images, perhaps they will become a little clearer. So these are like needles or rods, and the length is around 30 nanometers, the width or diameter is around 6 nanometers, and the cubes are around 20 nanometers size. So very different morphologies, very different nanogeometries. So we also looked at cobalt impregnated on these different morphologies. These are cobalt on the rods, and then these are cobalt on the cubes. And we can clearly see the CeO2. We seem to have a better dispersion over the cubes. These are some index images, perhaps they're not the clearest, but these are rods and these are cubes. As you can see, the ceria to cobalt intensity ratios, copper is coming from the grid, what that we use in electron microscopy. This is much more consistent wherever we are on the sample. Whereas here you can see that some areas have higher cobalt intensity, some do not. So clearly there is some agglomeration of cobalt over the rods. So better dispersion. We've also seen it through our dispersion measurements where we were using N2O as an adjuvant. X-ray diffraction also shows differences in the way the two crystalline planes different crystalline planes are exposed. These are just supports at the bottom and then the ones with cobalt on them. One important difference is rods, the CeO3 diffraction line is much more visible here, showing a poorer dispersion and more crystallinity for the cobalt species. But also, if you look at the relative intensity, we normalize it with respect to 111 crystalline planes. The rods, the tubes have a higher percentage of the diffraction intensity coming from 220 planes. How does this translate? How does it translate to performance? So this is a little busy, but we're looking at three different temperatures. The two catalysts, the ones on the left are rods, what's next to them are cubes, and different yields or conversion. So at 350 degrees centigrade, first of all, even at low temperatures, cubes are more active. These comparisons are done on an equal surface area basis. As we go higher, the conversion is increasing. But one important difference that we see here is that when you go to 450 degrees centigrade, the cubes have essentially only hydrogen and CO2. Very little CO, no ethylene, no methane. But if you look at the rods, we see a substantial amount of acetaldehyde left behind. Now, we looked at these in terms of selectivities at 400 degrees centigrade, so these are carbon-containing species selectivities, and you see acetaldehyde is much more visible over the rods at 450. The cubes, the acetaldehyde is going down. Rods have a lot of acetaldehyde, and same at 500 degrees centigrade. Of course, having been in this area long enough and having received enough criticisms about comparing selectivities at different conversions, we know better than that, so I told my students, you have to compare them at equal conversions, and we've done that. So this is an equal conversion, 50% conversion, comparing selectivities, and at equal conversion, we again have very significant levels of acetaldehyde remaining. So for some reason, the rods or the catalysts that are supported on the nanorods can take the first step, the hydrogen abstraction from the toxic species for acetaldehyde, but after that, it doesn't seem to go much further. And again, we have done some in situ, XF actually started reaction here, but if you look at the catalysts that are started out with oxidized conditions, so these are nanorods versus nanocubes, and you start out with only oxidized catalysts and they're gradually reducing. And here we are at the end of 60 minutes. This is with hydrogen, not under reaction conditions. And if you look at the cubes, after at the same amount of time under hydrogen, the cubes reduce far more readily. So the catalysts that are supported on the rods do not seem to reduce so easily as compared to the ones on the cubes. And actually, XAS also says the same thing. If you look at the, especially if you focus on this cobalt formation feature, this is nanorods, and here's the cubes. As you can see, by the time we reach 60 minutes, this feature has become much more intense. Now, one last thing, we have also we've done a lot of in situ IR work, but I'll just show this one. We picked a controlled sample of low reducibility, and we have done operando IR on this. So this is under reaction conditions, that will steam forming reaction conditions. So we start out with 25 degrees centigrade. You see some of the expected species. Certainly we see some CH3 vibrations or CH vibrations. But what I want to focus on here is this feature around 1730, 1735, which is really an aldehyde vibration. And it is clearly visible on the surface. We don't really see this. It is not a stable or easily detectable species over surfaces that are easily reducible. So this gave us some surface characterization backing to what we have seen through other studies. So to summarize, and this is a real summary, the final summary that will be in this section. So the catalyst surfaces can be tailored to provide better activity, selectivity, stability. We can control many different sensitivity parameters, support nanostructure, particle size, or specificity. Tailoring the support nanostructure to tailor 110 serial length helps to increase the dispersion, and as a result, it also helps with the accidental reduction and more reducible samples provide increased hydrogen yield and less spot products, especially acetaldehyd. So with that, I'd like to acknowledge the financial support that came from the Department of Energy. Again, Jeff Miller for helping out with the EXAF studies for SU Campus Electron facility. Again, Argonne National Lab for providing the mean time for those studies. And this is my research group. This picture was taken maybe a month ago. So this is what the group looks like in its most recent form. So again, thank you for inviting me, the organizers. Thank you for your attendance, and Burt, congratulations. Thank you. Thank you very much, Umit, and the floor is open for questions.
Have you run the support, the nanorod support by itself, and did you also see the high?
Yeah, we're just writing it up in the paper, so it's coming.
Okay.
Yes, yes, yes. And the results are very interesting. That's somewhat surprising. Yes.
I was wondering, the TPR of cobalt on Syria, if I remember correctly, one of the slide 12, I think. Was that cobalt on Syria?
I don't know if it was cobalt or cobalt. We had another support, so I think it was cobalt.
Because my question is if you saw indications that the Syria reduced as well.
Well, if you use large particle size Syria, it doesn't get reduced very easily. But if you have small particle sizes, nano-sized particle sizes, Syria gets reduced very easily. So we have seen that. The CPR patterns that I have shown were on larger Syria particles.
Do we have any additional questions? Because of timing, I will thank Professor Umit Ozkan one more time for this really nice presentation.